Good morning, good afternoon, good evening, everyone. Thank you for joining us for our next installment of the tinyML Talks. My name is Ravi Sivalingam with Qualcomm AI Research, and I'll be your moderator. Today, we have Atlas Wang from UT Austin talking about the lottery ticket hypothesis for gigantic pre-trained models. I hope all of you were able to attend last week's tinyML Summit. And if you didn't have a chance to watch it live, the recorded talks will be available on our YouTube channel, youtube.com/tinyml. Please go to that website and hit subscribe so you'll be notified when the videos are available. We'd like to thank our tinyML Talk sponsors, ARM, our tinyML strategic partner, DeepLight, Edge Impulse, Maxim Integrated, Kixo, Reality AI, and SynSense. Additional sponsorships are available. Please contact Olga at tinyml.org for more info. A reminder of our next tinyML talks on Tuesday, April 13th by Bernard Som, Machine Learning Product Manager at MathWorks. We'll be talking about deploying AI to embedded systems. The webcast start is the same time, 8 a.m. Pacific. Please contact talks at tinyml.org if you're interested in presenting at any upcoming sessions. All right, our speaker today, Professor Atlas Wang, is currently an assistant professor of electrical and computer engineering at UT Austin, leading the VITA research group. He's broadly interested in the fields of machine learning, computer vision, optimization. His latest interests focus on automated machine learning, learning-based optimization, machine learning robustness, and efficient deep learning. He has received many research awards and scholarships, including most recently an ARO Young Investigator Award, an IBM Faculty Research Award, an Amazon Research Award, Adobe Data Science Research Award, and 4 research competition prizes from CVPR, ICCV, and ECCV. That's from me. Go ahead, Professor Wang.
Thank you very much, Rob. And I'd like to take this opportunity to thank tinyML for having me and having organized such a great event. Today, I'm very delighted to share our recent work about lottery ticket hypothesis. While I'm not sure if it sounds familiar to you or not, I hope to bring to your attention this is a young arising field that may have a good deal of implications for tinyML applications, which we are thrilled about. So this the work I'm going to present today is done with my PhD student Tianlong Chen, my collaborators Jonathan Franke and Misha Cabin from MIT, and Shiyu Chang, Sijia Liu, and Yang Zhang from MIT IBM Worthing AI Lab. So without further ado, let's get started. I suspect people attending this talk are in general familiar with network compression and especially model pruning as its representative technique. Pruning, as we all know, has grown into a big field in deep network compression with many variants. And here I'm borrowing this finger from one online blog to show how many categories we have fall under the umbrella of pruning. In deep learning, we have to decide what to prune. Are you going to prune by element which lead to unstructured pruning? Are you trying to prune a channel so that lead to structural pruning? And when you do prune, do you want to measure the prunable element locally or globally? So that all constitute a question regarding to what to prune. And after deciding what to prune, you need to name the criteria, what element you believe unimportant and have to be pruned. That could be based on magnitude, that could be based on gradient, that could be based on any learning importance score, and that could be based on information theory metrics. So those are the second question we care about, how to prune. And traditionally overlooked but recently of great interest question is the third one, when to prune. Typically, when we talk about pruning, we talk about first we have trained a big model, and then after the training has finished, we treat pruning as some post-processing over the trained model. We hope to shrink its size, and meanwhile, restoring its accuracy by hopefully retraining. So so most of the prune we talk about fall under the after pruning time point, after training time point. But recently, more work has shown that you could done the pruning or adding specification process during the training process to gradually shrink out the redundancy. And you could even push that to the extreme and obtain a sparse neural network already improved at the initialization stage. And that should be a very appealing opportunity because we could have trained and test only in the sparse neural network domain and therefore have the all-around efficiency gain of sparsity. So answering this question, and especially putting pruning from after training to during training to before training, has been a recent trend that especially myself being very interested in as well. And of course, you could decide to do prune just as a one-shoot thing, or you could do a prune as an iterative multiple shoot thing. So answering those problems has characterized a big scope of prune, how many possibilities pruning could have. And today, my talk about the lottery ticket hypothesis will be following on the will be on the following coordinate. It will talk about I will mostly talk about unstructured pruning, although I will mention about its possibilities when we go from unstructured to structured. The pruning method will be mostly magnitude based. We'll talk about the algorithm specific. And for the time point, which is the most important one, we'll explore pruning before adding training. So you could get a sparse network, but trainable to satisfactory accuracy from the very beginning. And we will have iterative pruning to achieve that goal. So when we talk about lottery pruning, the coordinates we're actually looking at is iterative, unstructured magnitude pruning to obtain a sparse network before training. That is our goal. With that, let's zoom in our key topic today. I suspect many people sitting here may have heard about the name or alien heap associated with that of lottery ticket hypothesis. This is done by my collaborators, Jonathan Franke and Michael Cavan in ICLR 2019 and won the best paper of that year. The original paper did a very good definition of lottery ticket hypothesis, and I actually cannot find any good way to revise that. So I directly do a screenshot of the original text here. Lottery ticket hypothesis is defined as a randomly initialized dense neural network should contain a subnetwork, or maybe I say at least one subnetwork that is initialized in such a way that when trained in isolation, that sparse network with its initialization could be trained to match the test accuracy of the dense network it is extracted from. So although you have deactivated many of the neurons in the dense network, the remaining sparse subnetwork can still be trained separately and is as effective as the dense network. That's a very appealing possibility, as we already mentioned. So if we switch from training the original big network to this sparse, usually quite sparse. So in practice, when we do some large computer vision models, the sparsity we talk about could even reach above 90%. So talking about that sparsity, we know we're having a lot of promise in gain efficiency. And the winning ticket hypothesis gives you the following hope that such a sparse network could be trained to better, sometimes better, and often same or comparable within statistical range of the compared to the performance of the original dense network. And that does not come at any price of longer training. So you are training a sparse network and the number of epoch iterations does not increase. It does not become more difficult to train. And the trained network is naturally coming at a compressed form. It has notably fewer parameters higher than 90%. And the best of all, why it makes it different from training after the post-training pruning is this sparse network is trainable from the beginning, which make it a very special and very training-friendly form of pruning. You generally know that training a pruned network is not very gradient friendly because sparsity can kill your gradient and dead neurons also. But lottery ticket magically can overcome that problem. Okay, so I have bragged about all the benefit why we would love lottery ticket hypothesis. But all those things you will love about will only be based on one pre-assumption, that is, you know what sparse network you are going to choose. And this price does not come for free because choosing the sparse network subnetwork, although we assume that exists, choosing that out of the dense network is a highly non-trivial job and it is expensive. That has been the barrier that keep lottery tickets from being practical from this date of birth. So in the original lottery ticket paper, Frankie and Kevin have advocated using a very iterative magnitude pruning method. One of the most classical, old-fashioned, but flexible pruning method we have. So specifically, they would start from the dense initialized network. So they would start training the network for a while and do iterative pruning and do magnitude-based pruning after the network being trained. So you will get, just like you do every other pruning, you will get a sparse network. And what we do from here is we will keep this sparse connectivity map and map it back to the original initialized network. So everything that has been pruned in this trained network will also be removed in this original initialized network. And we will in this way we get a sparse network, and the remaining part, all the element, still preserves the original initialization, like the very beginning starting point. So we would repeat that process for several rounds, doing iterative until we reach a target sparsity. And in this way, the remaining sparse network with the sparse mask are accumulated during the iterations, and the initialization of the remaining sparse neurons to be still the same as the ones used in the very, very beginning dense network is becoming our sparse network and lottery ticket, and we call that a winning ticket. This is the network that Frankie and Kevin claim to be isolatedly trainable, with a sparse mask obtained by tedious training and with the initialization same as the very beginning. As you could see, this mask finding process is very tedious, actually more expensive than training the dense network from the scratch. So from the original paper, the lottery ticket is more like a very appealing theoretical phenomenon, but not very practically useful if we talk about machine learning efficiency, because you have to go that far to get that mask. But that is already very, I think that amazed many people, including myself, when this work just came out, because it went against our common wisdom that sparse neural network after pruning is not very trainable by gradient descent. With that big surprise, many work has followed this, and I'm not intending to include all the literature. I just pick a few literatures to provide people perhaps not familiar with the field with a context about what we have been, this community has been doing after the original paper being published. And from where we will, from those literature, I would also draw what motivates us to do the work I'm about to talk about today. So from the original lottery ticket paper, the authors advocate we should go all the way back to use the dense initialization, the initialization in the original dense network. The follow-up paper, also done by the same authors, propose stabilizing lottery ticket composites, and the key concept in that paper is the original initialization may not suffice to support lottery ticket composites in big network. So in the original paper, we talk about LearnNet, we talk about dataset like MNIST or CIFAR, but everybody want to be convinced though until we scale up to ImageNet and with big ResNet, right? So when do that big experiment, we find that it's very challenging for network to revive from the original initialization at high sparsity. But if we could give an extra push, which means if we could use some early stage training weight to roll back as a starting point of lottery ticket rather than the purely random initialization, that seemed to support the lottery ticket composites in large scale network. So the intuitive feeling here is lottery tickets is still a very high requirement training, and not always it can start all the way from the connect random initialization to the target solution. You may need to give a push and move the solution a bit favorably away from the initialization. For example, use the early stage training, the dense training. So you could, in that way, that you can connect the lottery ticket solution from the early stage weight. It's like you're giving some extra push to help the initialization. And some other work that shows that, the second paper, Deconstructing Lottery Ticket paper by Uber ITG Labs, shows that lottery tickets can even be effective to the extreme extent. You might be able to find a sparse mask from the random initialization network and assume the origin network is redundant and big enough. The sparse mask itself is an effective training. I'm saying that by meaning sometimes a very sophisticated sparse mask could be applied to a random network, and this randomly selected network without adding further training could already achieve much higher than random, actually highly non-trivial accuracy without adding training. In this way, this paper actually advocates an unusually important role of the sparse mask over dense network. That is, if the sparse mask is sophisticated enough, it can partially replace the role of weight training, and the mask itself is a strong enough form of information that make network behave like trained. And some other teams has found the deep network trend on one computer vision image classification dataset could transfer to the other. For example, if you have a ResNet, you train that on CIFAR10, and that sparse mask could transfer to the other. This is could transfer on classifying CIFAR10 images. I'd like to point out that this is a very important concept for lottery ticket. Actually, it inspires our work too. That shows the lottery ticket does not have to be specially tied to adding model architecture and adding specific data, because if you do that, every model and every data, you're going to redo the expensive iterative pruning process to get the ticket. And that greatly hurdles the possibility of training on the efficient training. But if you have any hope of reduce that mask, then just like the philosophy we like pre-training, with the adding extraordinary cost to fighting that mask could be democratized by reusing the same mask for different models and different data set, and that will make the expensive cost much more acceptable by this averaging sense. So this paper takes the first step away from that. And some other work shows that the good lottery ticket solutions are clustered together. And this is one of our early work called early bird tickets, showing that good lottery tickets does not have to emerge after the network training has been done. So it can be done actually in early stage of the training. So in the iterative magnitude pruning process, you don't have to finish every round of training until convergence. You can actually early stop each of the training round, and the ticket can still be found. And eventually, this is a more recent paper by the lottery ticket authors and advocate a following philosophy. And they extend the idea of they extend the research line of rewinding, and basically shows that the rewinding is actually appears very indispensable in very large networks. They did more benchmark studies, and they show that the matching initialization arising from the random initialization appear to be critical in fighting networks when fighting lottery tickets when trained from scratch. So I want to draw a connection line here and help you see the context where our MoCo arrived from them. From the stabilizing lottery tickets paper, to the drawing early bird ticket paper, to the early phase of network pruning paper, those papers and many of their symbolisms have showed that random initialization alone doesn't seem to always sufficient to support the lottery ticket composites. You will need to have somehow organized, somehow well-trained informative initialization to help lottery tickets scale up. This is one phenomenon I think have been agreed with by more and more people in this community. So that's a point one I want to convey to you. Point two I want to convey to you is lottery tickets so there are more than one lottery tickets, as shown by linear model connectivity and more other papers. And the lottery tickets also bear certain stability and transferability. For example, this paper shows lottery tickets can transfer for the same task, but across same task, same architecture, but across different data sets. That shows a promise that we could reuse the same task. If a lottery ticket mask could be reused as some kind of pre-training, then it will get us much closer to the goal of efficiency with lottery tickets. So the non-trivialness of early stage weight instead of random initialization and the need and the appeal of transferability of lottery tickets has placed the context where we started our work. Okay, so far I have been talking about the background for people not familiar with before, and now I'm introducing our work. The cutting point.
Hi, Atlas. Quick question, if I may interrupt at this time. You talked a bit about, they gave some examples of ResNet and ImageNet type of problems, scalar problems. But for tinyML, when people are working with very, very small networks, does this hypothesis still apply? I mean, like, pruning down from, can we prune down significantly from mobile net, efficient net type of architectures as well?
That's a great question. So first, lottery tickets can still be proof of the concept on mobile net. It can, so far we have been seeing smooth extension of that in both very large scale and very compact network. You're welcome to check our paper. And the second point, actually, I will specifically talk on is, I think lottery tickets will provide a practical bridge with the ongoing trend in using larger models, big pre-training in machine learning, and our tinyML practical demands. It could greatly sparsify those large models and make it close to the resource requirement we have on tiny devices. I will talk about in a later stage how it could be practically relevant. All right, thank you. All right, so yeah, so I'd like to make an advocate here. Just give me the time for like 7 or 8 more pages, and I will come to the tiny part. I know what I'm going to talk about now, especially on this page. It doesn't look like tiny, but I promise I will come to that keyword. All right, so the point where we have been focused our research on in the past 1 year is large pre-trained models. For many good reasons, people love them. It's becoming the central paradigm of computer vision, NLP, and many others. So we are talking about big models like Google's BERT, like simCLR, and the reason the GPT-3. I don't think GPT-3 is very close to edge application yet, but anyway, so that's a trend where people like people has been working to develop more sophisticated or more close to general AI functionalities. Though I totally agree with Raf that none of them look tiny at all, seems very distant away from tinyML applications. But what if we could make them tiny? I mean, those pre-trained models could do really sophisticated things. What if we could have a possibility to put Big BERT and GPT-3 on your mobile phone, and even closer? I'm not sure about the MCU, but even smaller than that. If we could make that tiny, we could bring more intelligence in on-device learning. And the lottery tickets will apply a unique rule here, and which will interest me. So, and why I'm loving lottery tickets for big pre-trained models and why it's relevant to lottery tickets. I have motivations from many aspects. The first thing is methodology-wise, I'm a researcher. I like new research questions. And as we said in the previous paper, previous literature told us, lottery tickets seem hardness to scale up using random initializations. But if I'm doing a pre-trained weight, I'm having very good weight that is not very random. That kind of remind us of the success of winning, right? So you could use early stage trained weight to support a lottery ticket to scale up. So if we base our lottery ticket experiment on pre-trained weight, would that be a natural starting point that get a lottery tickets existent, scaling up, and without do any rewinding from there? We could just have a pre-trained weight as a natural rewinding point. You don't need to do adding extra early stage training for that as well. So, and the lottery and the pre-training also give us a locality-based training, which in some of our theoretical papers we show will benefit lottery tickets, but I will skip over that. So methodology-wise, we're interested in finding lottery tickets in pre-training because it provides an appealing avenue to get rid of the extra rewinding step. And then go to a practical side. Lottery tickets could, if pre-trained models are useful, but they are big. If we could find extremely sparse lottery tickets in this big network and compress their size to compatible to mobile resource available, then it's a hope to bring those big pre-trained models on mobile devices. And the 2 more things I would like to emphasize here. What makes lottery tickets different from ordinary pruning or quantization we're using now? The key difference here is most compression methods that we are all familiar with are post-training approach. And we all know that after you do pruning, most of the pruning, you want to be able to train them much further. It's kind of fixed. The ink is dry. You just deploy them for testing purposes. But the beautiful gain of lottery tickets as a special pruning is you will have a lottery network that are independently trainable. And we'll show that remain relevant in the context of pruning as well. So what makes it significant for pre-training is the pre-trained model after finding lottery tickets can still be fine-tuned on extra data, on new tasks, on unseen domain data for personalization, for domain adaptation, for continual learning. It's still durable in the form of sparse neural network. So you not only enjoy the benefit of inference sparsity, you get the benefit of training sparsity as well. in the form of fixed sparsity mask. And that is why I think lottery tickets are significant in efficient learning. And with a very high sparsity, you could put that in a KB level storage of network. And we find that lottery tickets found in our way could generalize to many different downstream unseen tasks as well as the original dense network. And as I already implied, if I find a lottery tickets that I can generalize to many tasks, that is another good thing. That is another good transferability in addition to generalizing to different data sets. If I could pay a lot of finding a good mask for BERT on my cloud resource, and that BERT, after being masked, could transfer to all the 11 downstream tasks as well as the original BERT, then we would love it, right? And it doesn't sacrifice anything, and the mask could be reused by many different people and many different tasks. And we will not have a good reason to claim it's very costly due to the reusing. So those are the key philosophical motivations of why we want to explore in this setting. And now I'll quickly reporting you what we have found, which I in general find quite encouraging. So the first big subject we have studied is pre-trained BERT. Methodology-wise, we basically follow the iterative magnitude-based unstructured pruning method in finding lottery tickets originally. We just apply this technique on pre-trained BERT and see what we can get. In a nutshell, I'm summarizing the key observations in this one page for you. So the first thing is, using this original lottery ticket finding pruning approach, we can find matching subnetwork. Matching subnetwork here defined as a sparse subnetwork that can generalize as well as the original dense network on the tasks. So we can find such matching subnetwork or winning tickets at as high as 90% sparsity in BERT net models on standard glue and square downstream tasks, I mean all of the tasks. And the second, we can find those subnetwork as a pre-trained initialization, which means that the pre-trained you just do the iterative pruning, and after you find the mask, after keep training that, you will directly unroll back to the pre-trained initialization, and there is no need to record any during training weights. There is no early training weights available. Pre-trained initialization weights are good enough to do that. The practical implication is we are fully compatible with the official pre-trained weight of released BERT or others. You don't need to store an extra set of weights. It's just a sparse mask that you need to store. And we have verified those subnetworks found by IMP iterative magnitude pruning could outperform those found by random pruning or other pruning baselines. And the beautiful things, the most beautiful takeaway message is the third message. We have found that using the typical BERT pre-training task masked language modeling, the subnetwork found at as high as 70% sparsity, over 70%, is as transferrable as both BERT model. Which by that I'm saying the model trained by the same BERT training objective, when applied our found sparse mask, is performing as well as original BERT in every possible way. Every possible way means that it can be fine-tuned to, for example, the 11 NLP task on standard glue, and that perform as well as on all 11 tasks, perform as well as the original big BERT model. So you can see that so we call that a universally transferable lottery tickets. This is a very bold claim, because we could have the ticket work on task even unseen during training, and interestingly, we indeed show that it can happen. So that shows that the lottery ticket composites remain relevant and actually becoming more practical in the context of big pre-trained models, and no rewinding needed. So just a quick glance of main conclusions we have found in the BERT work. So we have done experiment to show winning tickets exist. And we show that, so I will bypass the concrete numbers and just help you go through a talk with the main experiment calls we have, including the paper. We show winning tickets exist on all the tasks. We show that the winning tickets could achieve higher sparsity while maintaining present accuracy than the typical pruning or random pruning baselines. We show that rewinding bring no extra value when pre-trained initialization is in presence. That's in contrast to all previous lottery ticket work relying on pruning to scale up to large models. And we find that the lottery ticket network can match the performance of a standard post-pruning on specific task, but while enjoy universal transferability. So you no longer need to fine-tune your model on each of the 11 NLP tasks and get its own sparse mask. This lottery tickets we are finding now is applied to the pre-training stage as initialization, and then you just tune the sparse network on each of the 11 tasks. They share the same sparse mask, and they match the performance of task-specific pruning. That's a beautiful result. We have attracted most deal of attention during the New York's conference. And we find that those winning tickets have certain transferability across the task. And we also observe some interesting patterns of the sparse network. So I'd like to put a few more comments here. So we find that the transferability in this BERT pre-training case seem to correlate most with the number of training example of the task rather than the specific type of the task. That's a really interesting thing. And give us a hint that on many of the BERT tasks, perhaps the fine-tuning downstream data cannot be yet caught enough. So for the mask language modeling task, the typical task people use to pre-train BERT, we find this task has the most abundant amount of data, and that task also becomes the best task we find in discovering the universal sparse mask that all other tasks can transfer from. So we don't have any research evidence here that a specific choice of task. We did some statistical analysis, but we didn't find the choice of task to matter a lot for how effective we could find a ticket in pre-trained initialization. We find the data volume in the downstream training to matter the most here, but that's just the BERT case. And many other conclusions and statistical analysis would be available from our paper. Without further ado, I would like to go to the second course of study. But before that, I want to know, Rav, do I get any question about this BERT part before I proceed to computer vision?
Yeah, actually, quite a few questions up already. One clarification is when you say pre-trained initialization, does that mean loading a pre-trained BERT model?
Exactly. Yes.
Okay, great. The other question is, did you try pruning the model after transferring in order to further sparsify the model, given that in the original task, a 90% sparse model was achieved?
That's a very good question. We haven't done that, but I could share with you another experiment we did, not including this paper, but we did it before. We have tried to do further quantization of our pruned subnetworks, and then do quantize our training to fine-tune the sparse network. We find the lottery ticket composites still support that. So that means, yes, there is room to further squeeze it for task specific.
Got it. Another couple of questions are related to hardware support for such sparse networks. So one question is, how does the sparsity gains map to computational gains on GPUs, which may be using acceleration of matrix multiplication of like full matrices?
Yeah, for hardware and practical platform question, may I request to defer after computer vision because I will talk about the hardware part in the last.
Got it.
I prepared some number. Yeah.
All right. That's all for now. We can continue and get back to later in the talk. Yeah. Thank you.
Sounds good. And thanks all for the questions. I will then talk about the second course of study and using pretty same philosophy, but actually towards more sophisticated conclusions. So this is to my more familiar computer vision field. We executed the same course of study, the BERT pre-training lottery tickets to computer vision pre-training models. But when we do that, it at least kill me a lot more CPU resource when I play with a BERT experiment, because computer vision really have more complicated when it comes to pre-training. For NLP people, BERT is, I know there are several models, but a few of them, and BERT is one of the dominating models. And when people are training BERT, we typically will use that one mask language modeling test, MLM. So everything tend to be standard and people agree on. But In computer vision, you know what I'm talking about, right? There are many pre-training ways, like people have a supervised classification as a pre-training on ImageNet. That's a typical ImageNet weight we're using. And now, given self-supervised training has gained its glory in pre-training, we have simCLR, we have MoCo, we have BYOB, we have SWAMP, and the reason the seed work from Facebook, and all those, there is no decisive winner, and they seem to all be good at something while not being universally sweeping over the others. So we have many computer vision pre-training ways, and many computer vision architectures, from ResNet to DenseNet to VGG. They're all in practical use and MobileNet. So, and moreover, computer vision downstream tasks are also very heterogeneous in terms of the prior or useful characteristics that it may want. For example, I use classification and detection as two prominent examples. In computer vision classification, image classification, there is one good thing that we always want, is called translation invariance. That means, for example, if the cat is located in anywhere, any specific location in this digital image, that image for classification, it should be treated the same, right? It should be still classified as a cat. But if I'm switching from a cat classification example to a detection example, I would want my features to actually be very sensitive to location change, because now what I want is the location. So what we're saying here is, for classification task, we would value shift invariance and the location translation invariance. But for other tasks like detection, segmentation, we would assume a location shift equivariance or sensitivity to that location shift. So those are just one example of many that different computer vision downstream tasks would want very different statistical features, properties of the feature, and there is no uniform golden standard. That creates additional difficulty why the transferability in general and for lottery tickets would be very difficult for computer vision, more than for BERT. And of course, BERT has been mostly doing fully connected models, and computer vision doing convolutional models. That would be another difference why the importing of BERT conclusion is not direct. So overall, computer vision has a diverse the pre-training objective, diverse model architecture, and a diverse downstream tasks that require a lot different in the properties that will make computer vision more challenging target in our subjective context. So again, I'm offering one page to summarize what I have found as a key take-home message. The first thing, overall, just sit back and relax. Our message is still positive and quite aligned with our BERT concept study. We have found that we are able to find a highly sparse network from pre-trained weights and in three forms of pre-training, using ImageNet classification, using simCLR, and use MoCo. And some of them could support, I'm talking about MoCo, could support quite a high sparsity while still being transferable to downstream tasks. And that transferability is not only identified across different pre-training ways, but also at downstream tasks. Very, very surprisingly, we find that the diverse requirement of downstream computer vision tasks do not create a big roadblock for transferability of lottery tickets. We find that those fetching network at a pretty high sparsity could universally transfer to ImageNet classification, MS CoCo detection, and segmentation. So that's a simultaneous transfer across dataset and across task. So that tells us there indeed exists very sparse subnetwork that can win them all. And then not only good for the same dataset, but also across dataset, but also across task, even in a complicated study like computer vision. And we also found that there exists a universally transferable ticket. So by universally transfer is that's exactly what I just said. You could transfer across the different data set and transfer across different tasks, and that will match the performance if you dedicatedly find the tickets on that data set and dedicatedly find the tickets on that on that downstream task, and you could reduce all the cost and advocate reusing of one mask that work for them all. And this is universally findable for different form of pre-trained initialization. That of course poses a lot of follow-up research questions for us about what's the intrinsic role of sparsity and why it can simultaneously take care of all those different statistics, but so far that's what we observed. I'm not going to dig into many details. So both this paper, same as last paper, is very experimental, and we report a lot of numbers, which, as you can imagine, kill a lot of GPU resources from my lab. But overall, I want to share a few uniquely interesting things we find in computer vision. So first thing we have find that is this sparsity mask we find in computer vision are very sensitive to structural perturbations, which means that if you shift some sparse mask, you just change some sparse mask from some non-zero element from here to there, that will break the performance quite suddenly. So the take-home message here is the sparse mask we find in this case is quite non-trivial. It's very sensitive to perturbation, which means it's valuable and it's very far away from being random. So the second conclusion we find is compared to BERT, which people generally admit one unified form of pre-training, computer vision, this diverse pre-training lead to diverse pre-training masks, diverse sparse masks associated with different pre-training as well. We have found that although each of them could display universal transferability at a certain sparsity, those masks those transferable masks corresponding to different weights are really very diverse. And we observe different distributions, the distribution of the sparse locations and the different properties. For example, if we could look at this finger on the left, we find that MoCo has if we do this lottery ticket fighting on MoCo pre-trained weight, MoCo has a very, very interesting trend to use a more uniform layer-wise sparsity ratios compared to simCLR and ImageNet supervised. Both the other two tend to have lower pruning on the lower layers and higher pruning on the higher levels, which is consensus to us, right? If you do pruning, you will tend to believe, well, we perhaps all know the first convolutional weight layer is very sensitive to compression. And the general trend is if you go higher, the pruning can be more aggressive because the lower level is reused across the classes, the high level is more class specific and more redundant. So this is reasonable, and that was reflected in our found sparse mask in simCLR and ImageNet supervised as well. But MoCo seemed to discover a different pattern. It's the best sparse mask tend to have a very uniform sparsity allocation across different layers. We are not sure why, but we could tell you that this seemed to give MoCo a competitive edge in transferring to detection and segmentation compared to simCLR and ImageNet. Actually, if you check the detail number in our paper, MoCo have the best transferability from classification to detection segmentation under our lottery ticket lens. So originally the pre-trained weight of simCLR and works almost as well as MoCo, but under the sparsity lens, MoCo is more robust to sparsity. And another extra bonus we observed from MoCo is it seemed to give you some, it seemed to give you some natural structured sparsity without you asking for that explicitly. What we observe is with the sparse mask we obtained from using unstructured pruning in MoCo weight seem to have a natural clustered property in the identified non-zero element locations. So by a very simple morphing, you could get a highly structured sparse mask out of iterative unstructured pruning when applied on MoCo weight. That's another interesting question. We haven't figured out exactly why yet, but I want to highlight that MoCo has some unique benefit when going through sparsity. That's at least what we have observed. It tended to do uniform pruning across layers. It tended to form structured sparsity even without being asked to do so. And it transfers better. Perhaps as a result of the two, it transfers better to segmentation and detection. So that's some to me very informative result we observed in experiment. And we also shows that just like the big tendency in pre-training in general, we find if we scale up with big pre-trained models, for example, from ResNet 50 to ResNet 101, we get the sparse mask more easy to find and it's more transferable. That's no surprise and aligned with the trend, but the trend of seems like there is no cap. You can endlessly increase your pre-training model size and get a better performance. And we find that that trend can still be strong even we will do a sparse masking on that big pre-trained weight. So what I'm saying is, if you train a very big model and do sparse masking to keep it small, that will give you better performance compared to train a smaller model and do less pruning. That's perhaps well-known concept already in deep network in general. And I'm telling you, this is still persisting when we come to pre-training and logic tickets. So after doing those, after introducing those two experimental studies, I want to spend a few pages to advocate why those are relevant for the tinyML community. I'm part of
before we go into the tinyML part, if you can take some questions about the previous slide. Actually, there was a question that I think you just basically answered. Is, in your opinion, which would achieve higher accuracy, a model prone to 0.05% density, or double size model prone to 0.025% density? And it looks like in the previous slide, you've basically said that training a larger model and reducing it to the same number of parameters is better.
Yeah, I'm basically an advocate of first training big and then going small. I think Google have a paper in ICML calling exactly that title. And I think we're looking at the theoretical aspect of why this happens. An intuitive concept of why is perhaps we could say it's the training over parameterized models. It's just like the older tricks or like the kernel tricks we're familiar with. We'll map the optimization in some high dimensional space that can make the optimization easier. So, essentially, after you have passing through this easier optimization trajectory, you are actually ending up a solution on low dimensionality, which kind of explains why over parameterized models do not actually overfit. This is called a W descent in the theoretical domain. So logic tickets is basically showing you there may exist some shortcut to directly go to that solution without first going high dimensional to do optimization and then map it back. But I think now the research question is, what is that shortcut passing through? But it does not disapprove the general value. You have to first scale up and then shrink it back down. And that's perhaps even more general practical.
So in your comparison and computer vision with like classification, detection and segmentation type networks, for like the backbone being equal, which networks do you feel are have you seen in your experience are more compressible in terms of sparsity?
I have to check back the papers, but the general impression I have is the bigger network, the higher sparsity you can achieve. We haven't actually compared the actual, the model capacity times the max sparsity achievable. I haven't really compared that numbers. But I suspect if you count that absolute number, a smaller model may still make sense here, because for all of the models, we could achieve high sparsity, 70%, 80%, 50%, 90%. And we definitely do not, yeah, even ResNet 101 with 99% is perhaps well, I cannot say no. I cannot say that for sure. Actually, I think we are able to achieve 97, 98% in ResNet 101 something, and that actually give a competitive edge of the sparse network we found in ResNet 50. I cannot say for sure. I need to check back the paper. And for people asking that, if you could send me a question, I could make sure I get the original numbers for you.
Sure. Right. Yeah. Please continue. We can come back to the other questions later.
Okay. Thank you very much. All right, so now let me spend a few upcoming pages to explain why I think this phenomenon may be interesting to tinyML practitioners. So I'm personally reading papers and seeing that speech recognition and simple computer vision are now already standard workhouses that you can run on even MCUs with the new TensorFlow Lite and some MCU level dev board. And I haven't seen much people doing really complicated vision tasks like doing segmentation and detection. That's perhaps not yet on the smallest like MCU level, but we definitely notice there is a trend to bring computer vision tasks to smaller and smaller models For example, I participated in a computer vision challenge called LPCV, Low Power Computer Vision challenge last year, simCLR, and that one was advocating to bring video text spotting that include detection, localization, and some simple NLP parsing as a working pipeline into a Raspberry Pi board, and I wanted to run in real time with low energy cost. So there is definitely a tendency of bring more complicated models down to the smaller board. So we're all confident in that, I guess. So how could lottery ticket have the sparsity bring ML to tiny? Then let's do some simple mathematics here. Let's try to pre-train a dense 32 bits ResNet 18, and the highest sparsity we could find in our computer vision paper is nearly 98%. So in that one, I remember we could gain performance loss less than 1% in terms of transferability. So in a relatively loose sense, we still call that a good sparse matching network. It's not an exact lottery tickets, but we call it a usable ticket. And with this highly sparse network, assume the backbone to be this one, we did a calculus here, and it will translate to, it was installed with 38 bit. If we store all those parameters in the sparse format, that will translate to below 70% KB storage if you store this model. So that's a storage. And notice that here we haven't done any, we haven't done any post-processing. We have tried an experiment, quantization is doable. You could do further quantization, and like someone has raised a question, is it possible to do some post-pruning if you want to overfit a task? I haven't tried that, but I think that's possible as well. So I would say this lottery ticket single alone is bring a very big network that is not typically within the consideration of tinyML practitioners to a usable range that looks quite practical to even MCU level device if you append it with some post processing. And if you do that, for more complex models like MobileNet, or maybe for many tinyML applications using just a relatively shallow network, lottery tickets could even further shrink down the resource cost with the extreme sparsity it can achieve. And further, I want to advocate that it comes at one extra benefit beyond all the compression method you are using now. That is, this sparse network can still be trained if you want to still train that further on the device for any good reason. That is good for continual learning. That is good for domain transfer. That is good for personalization. So for example, if you work on application of personalized health monitoring on a wristband or smartwatch or mobile phone, that sparse model could be your friend, because anyway, you need to customize to your users. So recently, you perhaps heard about deep network, and we talked about it as well. Deep network has that big trend of first pre-train a big model, and then fine-tune that big model, and then compress it small and deploy it to the final usage. So what I would advocate with our two papers is the following new regime. You should still pre-train a large model. Pre-training is most of our friends. But after pre-training, you don't need to do pruning and compression after the pruning step. What you could actually do is to find the lottery tickets sparse mask on the pre-trained weight directly. And that sparse mask pre-trained initialization is as effective as the original dense pre-trained model in terms of whatever downstream task you will be playing with. Therefore, it's naturally suitable for flexible deployment where continuous fine-tuning or personalization may be needed. So what the new regime I'm liking here is to switch the role of switch the location of compression and fine-tuning. The typical pipeline would first do pre-train and then fine-tune and then do compression, including pruning. But what I'm advocating here is you could do pre-train and then do direct lottery ticket pruning, and you do distillation, then and you do fine-tuning at the deployment, and you will enjoy the benefit of sparse network at whatever downstream task you want to fine-tuning towards. And this could be on device if for any good reason you want to train on device. So if I would advocate one take-home message from our work, this is the main home message I wanted to propagate to the tinyML community. The last page before I finish is to talk about how to translate that to hardware. I work on hardware-aware machine learning as well. So I guess I'm already educated that unstructured sparsity is not the best friend for hardware acceleration and energy efficiency. And for that, we have been looking at a three-pronged approach to bridge lottery tickets to practical platform. The first thing I want to mention is we have been in chat with sparse network teams in Google Brain, and they basically marketed us that they already have reasoned smartphone processor packages like the one they developed called XNNPark, published in CVPR 20. They are already able to accelerate a high unstructured sparsity. So if there is the unstructured sparsity, totally unstructured element-wise, is as high as 70 to 90%, then use the XNNPark, I believe they could achieve nearly 2 times the acceleration compared to dense network on an actual mobile phone. So I don't work on that compiler and the compiler side, but that's what I know they can do. So there is a possibility to still leverage a very high unstructured sparsity, and that high sparsity is the typical range lottery tickets is played at. So the second bullet I want to talk about is, although typical literature so far by default ties lottery tickets with unstructured pruning, some of our recent in-house work, not published yet, may have revealed there is a hope to find unstructured sparse lottery tickets. We are working on that, but I could hint with you that we have positive results with appropriately designed structure pruning. Lottery tickets still exist, and please expect some work from us in the next major upcoming conference. We will try to share the draft once it is ready. So the third thing I wanted to further remind, although it's not the main focus today, is we all know that sparsity is a long-term best friend of machine learning, and the benefit of sparsity goes well beyond resource efficiency or model compression. Now, when we talk about the model pruning, by default, we say, oh, that sparsity is for model compression. But in old-fashioned days, sparsity has been super useful in increasing model stability, in avoiding model overfitting, in increasing the data efficiency and the sample complexity of machine learning model learning. And some of our parallel works has shown that finding a sparse network could inherit those classical machine learning benefits as well. For example, we have found that recently we have a paper available on Archive showing that a lottery ticket sparse network will also be more data efficient to learn. So it will become a better friend for few-shot learning and data efficient training scenario as well. And we also have work that shows the sparse network could behave like naturally regularized to avoid overfitting when do domain transfer from a pre-trained model to a new domain. It can avoid catastrophic forgetting of the pre-trained knowledge. And another application we recently worked on is federated learning. So we are now extending lottery ticket composites in the federated learning case. And as many of you may immediately realize, a sparse model is not only more efficient when training on local device. And now if I'm transmitting just a delta model of a sparse mask, and the sparse mask is pre-selected, I'm getting a big benefit of saving bandwidth with communication benefits as well. So this is a great example of killing two birds with one stone. With the sparse network properly identified, you could not only train and inference on local agent more efficiently, but also optimize communication efficiency because only sparse weights deltas need to be transmitted rather than the full dense weights delta. So that is another ongoing work we have on house that we hopefully will roll out in a few next months. Overall, so that is concluding our so that comes to the conclusion part of my talk. So our work has been published in 2 papers. Our BERT papers are published in last year's Europe. Our computer vision papers was just accepted in CVPR. We have a project page done by my excellent, super capable PhD student Tianlong, who should take the main credit for those works. And all our research code, including those 2 papers, actually every other of our papers are publicly downloadable from our group's GitHub. You will be able to find the pre-trained models, all the experimental code we have, and the tools we developed for lottery tickets from our GitHub. So our work has been thankfully covered by some leading tech media like MIT News wrote a very nice article appraising our work. With that, I think I'm ready to conclude my talk, and I hope you enjoy that, and we hope we could all win the big lottery with the efficient applications we are loving about. Okay, so Rav, take it away. I'm done with my talk.
Thank you very much, Atlas. That was very good. You brought it from really large networks all the way down to tinyML, and I think that's really great for our audience. We have a bunch of more questions. One of the things that I wanted to ask about is related to quantization. All the lottery ticket hypothesis you've talked about, concerns pruning. Is there a similar lottery for quantization? Now, that's one question. And the flip side of that question is, by doing a lot of pruning, introducing more sparsity, does that make the network less quantizable if you're trying to bring it down to 8 bits, or does that affect the quantizability of the network?
Okay, I think both are really good questions. So first, as I said, we find that the lottery ticket network we have found now is quantizable to a certain extent. We have experiments show some of them could be quantized to 8-bit at the very least. We haven't tried deeper like binary, but there is a room. We actually have another parallel work showing quantization may lead to similar conclusions of lottery tickets as well. That's again some unpublished experiment, but the main idea is you could treat quantization as a softened version of pruning. Because well, if you call removing an element as a 0-bit quantization, then you can see that all the quantization will play with as a continuous transition between fully preserved and fully quantized. We are taking this view and redo lottery ticket composites, and we find that yes, there is a hope as well. We just haven't finished our experiment, so you are hitting some of the right point we're working on. And eventually for the question whether it's worthy to go all the way to extreme sparsity and whether that sacrifices the benefit of how deep we could quantize, I haven't tried the exhaustive experiment, but I feel what you said makes sense and maybe plausible. And I think in general, to make maxing out of the resource efficiency, you always want to trade off between all the availability you have. You quantize pruning or knowledge distillation or even AutoML. We haven't jointly considered that those in the lottery tickets literature, but we do have other works showing that a joint optimization of pruning and quantization and knowledge distillation formulated all together rather than separate steps could boost model compression performance. So I won't be surprised if similar techniques could show, if we, for example, we already say quantization, it could be looked in a unified view from pruning. So I won't be surprised if we combine them together and do the use that to replace a simple yes or no pruning to lottery tickets, we can find more jointly optimized versions of lottery tickets. And I think that implication and this combination with hybrid precision hardware would be of great interest for research too.
Thank you. So some other questions, I think this one you've answered a little bit in the previous slide, is whether hardware support exists for sparse networks. You talked about XNN pack. Is there any other, any comments about sparse networks being faster than their dense versions, considering their regularity?
Yes, I think that one I have already mentioned about. We haven't, to be honest, we haven't implemented the lottery ticket on XNN Park. We're just talking to the team. And from what they observed in their paper, I think our sparsity should map to double acceleration also.
Got it. Another question about CNNs versus transformers. CNNs use convolutional layers, so there's high coefficient reuse. But transformers use mostly fully connected layers which have low coefficient reuse. So how does the sparsity or sparsifiability compare between CNNs and transformers? Okay, that's a very good question. I do agree that the sparsity, and so sparsity is a very inherent thing. It comes from the data. As long as we use over-parameterized model, whatever model form should display some kind of sparsity. That's first. But secondly, I agree that transformers and CNNs come sparsity from different places. Like CNNs would learn the natural sparse maps and the natural sparse filters. But for transformers, I think the sparsity comes in the forms like, for example, the multi-attention head. Some of that
attention head may be redundant. Second, in the self-attention map, not all the locations need to be attended. Only some locations need to have. So if we are perhaps learning some activation pattern from the data that some only need to attend to some key only need to attend to some other anchors. So that's that's the sparsity we observe most from the BERT models, and also recently in virtual transformer models. But overall, I think as long as I said, you use over parameterization and you use high dimensional data, sparsity is always there in some form.
Got it. We have time for one last question. Is about transferring the lottery model to segmentation tasks. What architecture did you use for segmentation? Because usually there is a relatively large accuracy drop.
Yes, I remember we are using that experiment. We're using ResNet 50 backbone, and we are using a DeepLab v3 built on the same backbone. So after we have found a lot of tickets on ResNet 50, we directly plugged into DeepLab v3 and continue tune.
Got it. Thank you. That's all the questions we have time for. Any further questions, we can take them to tinyml.org/forums, and the professor can continue answering the questions offline if you're interested.
Yeah, and I would also be very accessible by my emails. I'm usually quite responsive if in case you have any question.
Thank you very much, Professor. Once again, we'd like to thank our tinyML Talk sponsors, ARM, our tinyML strategic partner, DeepLight, EdgeImpulse, Maxim Integrated, Kixo, Reality AI, and SynSense. ARM, bringing the open source CMSys NN to unlock the power of neural networks in Cortex-M class microcontrollers. DeepLight, we use AI to make other AI faster, smaller, and more power efficient. EdgeImpulse enables developers to create the next generation of intelligent device solutions with embedded machine learning. Maxim Integrated, bringing advanced AI acceleration with the new Max 78000, which implements AI inferences at low energy levels. Now the edge can see and hear like never before. Kixo AutoML, automated machine learning platform that builds tinyML solutions for the edge using sensor data. Reality AI, with pre-built edge AI sensing modules plus tools to build your own. Add advanced sensing to your product with edge AI and tinyML. SynSense builds sensing and inference hardware for ultra-low power embedded mobile and edge devices. Just a reminder of our next tinyML talk on April 13th from MathWorks. Thank you, everyone, and see you next time.